Okay, so it's my pleasure to introduce Mikhail Lyubich from Stony Brook. It's a celebration of our department, of the strength of our department. He will be a winner in the ICM, and he will give us a preview of the talk. So his title is Low-Dimensional Analytic Dynamics from one dimension to two dimensions. Okay.
Yeah, rather thanks a lot for the invitation and for giving me this assignment, what to speak about. So, yeah, I remember someone said that the city of Rome has this magnetic power that someone can come to the city just for one day visit and stay there for life. And it seems to me that Stony Brook is my Rome. So it was exactly, almost today, exactly 25 years ago, when Jack Milner sent me a letter to Leningrad inviting me to visit briefly Stony Brook, the Institute for Math Sciences, the MS, which was just founded at that time. And so eventually I came for a fairly brief visit, and I still cannot escape from here. Yes, so and what I would like to tell you today is what I have been doing here these 25 years. So, and believe it or not, but basically I have been busy trying to understand the quadratic family. And it keeps disappearing. So I'm trying to understand the quadratic family. And so, well, don't leave immediately, please. So it could be more interesting than you think. And of course, so from the elementary school, we think that we know what the quadratic family is. So we have some picture of this type. So it is x squared plus c. And it is not exciting enough to keep someone motivated for 25 years. But one can think about the quadratic family in a very different way. And I hope that the picture will come back. And it is not coming back. So. So is Josh? It is a dynamical picture of the quadratic family, and I will try to tell you how to understand this picture and some other related pictures. So what is the meaning of the dynamical picture? So what dynamical system is for us today, it will be just a map from some manifold M to itself. So f to the nth will be n-fold iterate. We have some semi-group of a semi-group acting on M, or group acting on M if f is invertible. So, and we try to understand the phase portrait of this dynamical system. So how the space of orbits look like, and how these orbits, so how this phase space depends on parameters of the system. So that is our main goal. And for today, dimension of the manifold will be either 1 or 2, real or complex dimension. And our main examples will be either just the quadratic family, it is in dimension 1. It will be an endomorphism, clearly, so non-invertible, so we have a semi-group action here. Or it will be a Henon family, which acts in R2 or C2, and it is the family of automorphisms, or it is invertible maps of C2. And we try to understand this, guys. So, but first of all, let me give you some conceptual background. So, and a good point to start, as Poincaré wrote long ago in the beginning of the dynamical systems theory era, so that the only opening through which we can try to penetrate to the domain of dynamics is to look at the periodic points, or in fact more especially we can look at the fixed point to start with. Periodic points, of course, the points which return back under some iterate. So let us take a look at some fixed point. So here is this fixed point, and assume that this fixed point is saddle, that the differential has two multipliers, one of which is inside stable multiplier. Inside of the circle, there is a stable manifold corresponding to this multiplier. Another one is unstable. There is unstable manifold. So the orbits here exponentially fast converge to this point. The orbits in the unstable manifold exponentially fast, so repelled from this point. And the interesting thing that already, so Poincaré faced, then these manifolds can intersect, creating homoclinic points. And then, so it is just, I depicted two intersections, but then you should start iterating it, and you see a lot of intersections, and they are intertwined in a very intricate way, which made Poincaré desperate. So he wrote that I'm struck by a complexity of this figure, which I'm not even attempting to draw. Of course, he did not have computers at that time. But so a few decades later, like in 60s, there was actually a very good model found for this complexity, which is called Smale-Hochschild. Not for the whole complexity, but at least capturing part of this complexity. So you can see here that there is some Hochschild type figure here, and Smale suggested such a model. So let us consider some box which is mapped. So, well, you can imagine that it's a global map in the plane, but restricted to the box. So we obtain such a, so the image of the box is such a Hochschild, and you should think in the following way. You contract this box vertically, you expand it horizontally, and you bend it in such a way to obtain this Hochschild. And it is very important that the tip of this Hochschild is outside of the box. So this detail is extremely important, and it makes this map quite tractable. Namely, if we consider all the points which never escape from this box, it will be a counter set. This set of dots is supposed to depict a counter set. And on this counter set, the dynamics can be described quite explicitly. Though it is complicated, chaotic dynamics, it can be described in some symbolic terms and very well controlled. But an important feature of this dynamics on this counter set is hyperbolicity. That is one of the key words, some crucial notion introduced in 60s due to work of Smale, Anosov, and others. So, and basically, without formalizing it, it means that there are two foliations, stable foliation and unstable foliation. And along the stable leaves, the orbits get together exponentially fast. And along the unstable leaves, they get apart exponentially fast. It is like in the case of one fixed point, but just now, instead of the fixed point, we have the whole counter set. And we have such a expanding and contracting direction, so uniformly over this counter set. And the remarkable feature discovered by Anosov, then this all complexity is actually robust. It is preserved under perturbations. This property, which is called structural stability. If we perturb this horseshoe, then the invariant set J0 will be perturbed a little bit, and the dynamics on the perturbed set will be topologically conjugate to the original dynamics. So it was a hope. So it's a very nice feature. So we have these hyperbolic systems, which are so complex. They are robust. So we have an open set of hyperbolic systems. And it was some brief moment of hope that actually any system can be approximated by such a hyperbolic structural stable system. But this hope very fast disappeared. And there are several phenomena which are responsible for this disappearance, but most impressive one is this Newhouse phenomenon, is that in dimension 2, so starting with dimension 2, it's important, one can find some domain in the space of diffeomorphisms on surfaces, which is densely filled with maps that have infinitely many coexisting attracting cycles. This sinks stands for the attracting cycles. And infinitely many coexistence attracting cycles is incompatible with hyperbolicity. If to give precise definition of hyperbolicity, this would be obvious. So, so it means that hyperbolicity cannot be dense, at least beginning with dimension 2. So it was a moment of desperation, actually. It looked that the dynamical systems are too complex at all to have any reasonable view what is going on generically. So, and well, so it was development mostly, it was initiated by Smail's work to a large extent, and Smail was motivated by, motivated in big way by developments in topology in 60s and 50s, 60s. So, but in parallel developments in Moscow, or in the Soviet Union more generally, it was realization that one should not use only topological methods. Topological methods are not quite adequate to capture complexity of dynamical systems. One should invoke methods of ergodic theory of probability. And this point of view was very strongly articulated by Kolmogorov in 50s. So, it was actually his talk at the ICM in Amsterdam, where he said that the approach from measure-theoretic point of view seems to be physically natural. So he sort of contrasted it to the purely topological approach. But he recognized that it faces problems, what is the right choice of measures, particularly in the infinitely dimensional space of parameters. It's unclear what is the right choice of measures, but actually in the phase space, could be also problematic. Well, so this development, this point of view of Kolmogorov led in the Soviet Union, in Moscow, led to development of this measure-theoretic point of view, particularly by Arnold Sinai's school, and in particular to the notion of non-uniform hyperbolicity. Now, instead of invariant set, this horseshoe, we have an invariant measure, and almost everywhere with respect to this invariant, for almost all points with respect to this invariant measure, we have stable and unstable manifolds with this exponential contraction, exponential expansion in the unstable directions. But everything depends only measurably on the points. All constants are non-uniform, but only measurable. So, but still, this situation can occur, and it is quite frequent situation. So there could be some hope that this kind of picture could be observed typically. So it's not so rare as uniform hyperbolicity introduced by Smail. Well, but now the question, so what is a good measure? So the problem is that the measure itself, invariant measure itself, can be singular with respect to the Lebesgue measure. Lebesgue measure is physically natural measure. So we have manifold. We want to understand how the orbits, typical orbits with respect to the Lebesgue measure behave. That is physically meaningful measure. And the invariant, the Lebesgue measure may not be invariant, and may not be absolutely continuous invariant measures. So which measures are meaningful? And then so eventually this notion of a physical measure was worked out. And so we have an invariant measure which may well be singular measure, but this measure governs the behavior of almost all points x with respect to the Lyubich measure. So if you take the typical point x with respect to the Lyubich measure, you consider the forward orbit of this point, and you start to average this forward orbit. So then it will be equidistributed with respect to our singular, maybe singular, invariant measure. So in this way, so this measure gives an asymptotic distribution of the behavior of the set of points, which are representative from the point of view of physical measures. That's why this is called physical measure. And there is very, very important particular case of the physical measure, that is SRB measures for scenario and Bowen. So this measure is hyperbolic in the sense that I just defined before, so in the sense of oscillated and paced. So there is this stable and unstable manifolds, measurable family of stable and unstable manifolds. But also there is this very important absolute continuity property that if you disintegrate, if you condition this measure to the unstable manifolds, then it will be absolutely continuous with respect to the Lyubich measure on the unstable manifolds. This absolute continuity property makes this measure physical. So this is a very important class of measures. So the notion emerged in the 70s. And this is measures which are chaotic. So there is hyperbolicity for these measures. But still they attract and govern behavior of big set of points from the Lyubich point of view. And then there is an associated notion of physical or SRB attractor. It is just an invariant set A, which is the support of some physical or SRB measure. And in particular, so the notion of attractor, that is a notion which fascinated people in the 70s. There was this famous Lorentz attractor, or it is the picture of the Henon attractor. So it is just for this simple Henon map that I drew you for some parameters. It was discovered that there is fairly complicated invariant set so that the orbits converge to this, asymptotically converge to this set. And actually, the set is more complicated than it appears on this picture, because if you start to magnify here, you will see a lot of structure, and very complicated and intricate structure. So that is what was called in 70s strange attractor. So we have a notion of physical or SRB attractor, which is an attractor which is support of this physical or SRB measure. And then gradually, so some fundamental conjecture in dynamical systems emerge. So due to works of Jack Milner, Palais formulated certain conjectures emphasizing importance of the finiteness of this number of attractors, of physical attractors. And here, let me put here some fairly strong version of this conjecture. It is safe. I think nobody would be able today disprove this conjecture. So let me put this safe, but let me put this strong version which says that for typical F, there exist finitely many SRB attractors, so these hyperbolic attractors which govern behavior of many points, and so altogether these finitely many SRB attractors govern behavior of almost all points. So if you take a typical system, then there are only finitely many attractors which support these nice measures and which attract almost all Lyubich points. So that is, let me call this fundamental conjecture. And of course, there are many questions here. Well, the crucial question here is what is typical F? That is exactly these doubts by Kolmogorov, because F belongs to some infinite dimensional space. And so what is typical? And we don't want a purely topological point of view. And actually, Kolmogorov himself suggested a probabilistic point of view to the notion of typical, more not purely probabilistic, but mixed. His suggestion was like that. Take a generic, in some topologicals and generic one-parameter family of maps, and so establish something for typical parameter values in this one-parameter family, typical or finite parameter family. So that was his idea. So try to understand infinitely dimensional space by taking slices, by taking finite parameter slices, and understanding what is going on in these finitely parameter slices. And in these finitely parameter slices, of course, there is a natural notion of Lyubich measure. So we will see that in some cases, at least, this point of view works beautifully. So, okay, this will be our fundamental conjecture, and the discussion will be rotating about this conjecture this way or another. Okay, that is our Henon attractor. Another idea, which is superficially unrelated to the previous ideas which emerged in 70s. So it came from physics originally, so people can recognize the familiar notion of renormalization. To dynamics, it was transferred by the work of Feigenbaum and Charles Rarr, who is here, and Couler. So, and it became one of the most powerful ideas in contemporary dynamics. So, oops, so what I'm doing. So that is the idea of renormalization. So what is that? So dynamical renormalization is much better defined than the renormalization in physics, but still I will start with some very general and a little and quite vague idea. Assume that you take some piece of the phase space, and you would consider now, you would like to understand, it's a small scale. You select some scale, and you would like to understand your dynamics in this scale. What does it mean? You consider the first return map, or some return map, to this piece of the phase space. And then you somehow make change a variable so that this little piece starts to look like the original piece. And you do this rescaling, you obtain new dynamical system. Let us call it RF, so renormalization of F. And then you would like to understand this system in smaller scale and do the same thing. So here is the first return map. You rescale it, maybe nonlinear or linear, and you obtain the second renormalization, etc. And so you have, maybe you can repeat this to infinity, and so the system will be infinitely normalizable. Maybe you should stop at some point. It depends on a particular circumstances, particular definitions, particular space of maps you're interested in. So why it could help? So of course, if you, it is clear that to control small-scale structure of your original dynamical systems is more or less the same as to control this sequence of renormalizations. How to control the sequence of renormalizations? The first crucial property that you want to have is a priori bounds. So you want this system belong to some particular space which is compact, sufficiently small space of dynamical systems. And if you can establish this is very big if, but if you can establish this, then you give some uniform control of your system in all scales, and it is great. And then there is this fantastic picture, also coming from physics, so but from people in dynamics at that time, it was a complete surprise that in some circumstances you can anticipate even much more than precompactness. You can anticipate that there is a fixed point for this dynamical system. So something which in this scale looks exactly like in the original scale, of course, after this rescaling. There is a fixed point of renormalization. Now it is this now is the whole big space of maps under consideration. It's big infinitely dimensional space of maps. And here we have a fixed point. And this fixed point could be a hyperbolic fixed point in the sense we discussed in the very beginning. So it has a stable manifold, but now it is infinitely dimensional manifold. And it has unstable manifolds, which desirably should be finite dimensional. And actually, in further discussion, it will be just one dimensional. And if you have such a picture, and of course, why you anticipate to have such a picture, I think that the reasons for Charles and other people who introduced this picture to dynamics was physical reasons. But if you have such a picture, you really have a universal control of your dynamical systems in your space. Namely, the small-scale structure of infinitely renormalizable systems, which are in this stable manifold, will be controlled fully by these fixed points. They will be the same as the fixed points. They will have all of them will have the same small-scale structure, such universality of the dynamical structure, small-scale structure, and parameter structure will be controlled of this unstable manifold. Because if you take another family, finite parameter family, one parameter family, say if it is one-dimensional, or family of maps, then the bifurcations in this family will mimic the bifurcation in this unstable manifold. So it is fantastic picture, but of course, so why should anticipate this picture? It turns out that there are some situations when this picture actually occur and can be actually justified. So, and finally, So to conclude this introduction, so the another sort of remarkable thing which happened in already a little bit later in 80s, 90s is a merge of real dynamics and complex dynamics. Complex dynamics, holomorphic dynamics, it is classical field, so which was founded in the beginning of 20th century by Fatou and Julia, but it existed completely separated from the mainstream of dynamics. Absolutely, from the Smales, Anosov, Sinai development, complete separation. And in 80s, 90s, there is a merge, and it fully justified, this merge fully justified this, this principle by Penleve and Hadamard. Then between two truths in the real domain, the easiest and shortest path quite often passes through the complex domain. So let us try to take this shortcut through the complex domain. So this will be, that is why, according to this principle, I will start the discussion with some basics in holomorphic dynamics. And I will restrict myself, as I promised, just to one specific family. The complex quadratic family, z squared plus c. Now z is a complex variable, c is a complex parameter. And what are the basic objects? There is a basin of infinity, basin of just the set of orbits which escape to infinity. There is a field Julia set, the set of orbits which don't escape, so it is complement of this basin of infinity. And there is a Julia set. It is the common boundary between the basin of infinity and the field Julia set. And here is a typical picture. So here is the basin of infinity. This orbits here escape to infinity. This black Dodis rabbit is a field Julia set. Here the orbits stay bounded. And the Julia set is this complicated counter set, not counter, fractal set, complicated fractal set that separates basin of infinity and orbits which don't escape. Also, this particular example has this very interesting feature that it has an attracting periodic point, namely 0. It is here. It is 0 is the critical point for the quadratic map, as we all know. So 0 goes to here, then goes to here, and then comes back exactly to itself. So we have a periodic point of period 3, and this periodic point is attracting. And actually, so all orbits in the interior of this rabbit, they attract, they accumulate on this cycle of period 3, going around, 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 accumulating closer and closer on this cycle of period 3. Such quadratic maps are called hyperbolic maps. You can ask why hyperbolic. We had already one notion of hyperbolicity when there is a stable foliation and unstable foliation. Why this property corresponds to hyperbolicity? There is one good reason. Then when this happens, when there is an attracting cycle in the quadratic case, then on the Julia set there is a uniform exponential expanding dynamics. If you take 2 points on the Julia set, then they will get apart at uniformly exponential rate. So, and in this case, because it's one-dimensional situation, it's complex one-dimensional situation, we don't have a attracting direction, we have only expanding direction. So this hyperbolicity, notion of hyperbolicity reduces only to expansion, or actually for this periodic point, for this matter, it reduces to contraction, but we cannot have them simultaneously. So it is a very, it is a correct one-dimensional analog of the hyperbolic maps in the sense that I defined before in the invertible two-dimensional situation. Okay, so here is an example. Let us go back to our main basic definition. So I already defined hyperbolic maps. The quadratic map is called hyperbolic. When it has an attracting cycle, it can have only one attracting cycle. It is classical theorem by Fatou and Julia. And in this case, the dynamics is exponential and stable on the Julia set. And it is a very important class of dynamical systems. And there is a Fatou conjecture which goes back to Fatou. So it was not so explicitly stated, so clearly stated, but it is these days called Fatou conjecture, that actually in this one-dimensional, complex one-dimensional situation, the Smales insight was correct. Hyperbolic parameters should be dense in the parameter space. We have just one parameter space here, and if we consider all the maps which have an attracting cycle, then the hyperbolic maps should be dense in this space. In one-dimensional situation, this conjecture stands a chance. Okay, it's still conjecture, let me say, and I will tell you more about progress in this conjecture over the past 20 years. Okay, so but next very important notion is the Mandelbrot set, and it is related to the basic dichotomy also in the quadratic case. In the quadratic case, everything looks a little bit easier than in general, but main difficulties are the same in a way, but some basic definitions a little bit easier. And so there is a basic dichotomy for the quadratic maps. The Julia set is either connected or it is a totally disconnected set, a counter set. And then we can just so try to understand this dichotomy looking in our parameter space. So look at our parameter plane and mark those points for which the Julia set is connected. And this set is called the Mandelbrot set, and that is the one that I showed you in the very beginning. So that is the Mandelbrot set. It is the parameter plane for the complex quadratic family z squared plus c. Here in this blue region, the Julia set is a counter set. Here in the red region, and actually it continues here, so this all belongs to the Mandelbrot set as well. And for all these parameters, and it goes here, for all these parameters, the Julia set is connected. So the parameter, that this rabbit that we have seen before, when there is an attracting cycle of period 3, the parameter is right here in the center of this component. Here in the main cardioid, that is main cardioid of the Mandelbrot set, here our map has actually an attracting fixed point. It is hyperbolic maps that have an attracting fixed point. Here there is an attracting cycle of period 2. Here there is an attracting cycle of period 4, and etc. There is this cascade of Dublin bifurcation visible here, 4, 8, etc., which accumulates to the parameter which is called the Feigenbaum parameter. But there is a lot of invisible stuff. But so if you go to on internet, you can easily just see movies and beautiful pictures, magnifications of this set. It is really fascinating structure if you penetrate to small scales of this Mandelbrot set. I am sure many people have seen this many times. So, but we certainly would like to make some sense, mathematical sense of all that. But basically, Fatou conjecture says that all components of interior of this Mandelbrot set consist of maps which have an attracting cycle. So all we can find on the computers, all components of interior of the Mandelbrot set that we can find of the computer are such, but there could be some queer components hidden, not visible on the computer, where there is no attracting cycle. Then the Fatou conjecture would be wrong. But there is a very strong belief and evidence that it must be correct. Okay, and there is a related, which though superficially it is not clear at all why it is related, fantastic conjecture put forward by Doherty and Hubbard in 80s, and it is called abbreviated MLC. And the meaning is that the Mandelbrot set is locally connected. And what Doherty and Hubbard discovered that if this is true, then they can construct, and actually with some input from Thurston's work, they can construct a precise topological model for the Mandelbrot set. This fractal set, which is so complicated, admits a precise topological model as long as it is locally connected. And this topological model would imply that there are no of these queer components, that the hyperbolic maps must be dense in the Mandelbrot set. So it would imply Fatou conjecture. So this conjecture supersedes the Fatou conjecture and basically gives a complete understanding of the complex, would give a complete understanding of the complex quadratic family. This conjecture is still open. So, but a remarkable discovery that this conjecture, MLC conjecture, so not only it is in deep way related to the Fatou conjecture, it is in the deep way related to the renormalization theory that I alluded to. So, and in this case, the space of maps for which we define our normalization is so-called quadratic-like maps. It is like restrictions of quadratic maps. It's like you have one disk and some map onto the bigger disk, which is a holomorphic branch covering of degree 2. So such maps are called quadratic-like maps. And assume that you have some quadratic-like map, and it is a Julia set of this quadratic-like map, which is by definition defined the same way as for quadratic maps, very similar way, very easy to give definition. And assume that you can find some domain here which goes around, and under p-fold iterate comes back as a quadratic-like map. I want you for a second to appreciate this, because f to the p is the map of degree 2 to the p. It is polynomial of very high degree. However, you find very nice domain here, such that restricted to this domain, you obtain a quadratic, again, the map just of degree 2. And you rescale this map to the original size, and it is your normalization, very well defined. Of course, some maps are normalizable. I skip some technical details. Should be some technical conditions put also, but I skip them. So well-defined normalization. Some maps are renormalizable, some maps are not renormalizable. So some are infinitely normalizable, some are finitely normalizable only, etc. So you can sort of now classify all maps in this way, but you also can attach certain combinatorics to this renormalization. It is the way how these domains sit in so you have this domain goes around, and you have all these domains sitting in some way in the big Julia set. There is some tree. There is this tree which shows how these domains are embedded into the big Julia, are located in the big Julia set. And this tree is responsible for combinatorics of your renormalization, just for this type of renormalization. And it turns out that there is a wonderful, so we can ask ourselves immediately a question. So what are those parameters, those quadratic polynomials, which are renormalizable with this particular combinatorics? And the answer is that it is some little copy of the Mandelbrot set inside of the Mandelbrot set. So inside of the Mandelbrot set, you can find many little copies. One of them is visible here. Some of them are not so little, so that is a so-called little copy corresponding to doubling renormalization with period 2. This is little copy corresponding to tripling renormalization with period 3. But these copies are called satellite copies. They attach to the main cardioid. But there is many, many copies. Here is the most visible copy, which is not attached to the main cardioid. Still small here, but all over the place. If you start to magnify, eventually you will hit some little copy of the Mandelbrot set, which looks exactly like the original Mandelbrot set. Let me show you just one of these copies coming from somewhere. This environment is some part of the Mandelbrot set, and it is just some random copy. You see that it looks exactly like the original Mandelbrot set. And it is exactly the set, the maps inside of this copy, the parameters inside of this copy is exactly the maps which are renormalizable in this quadratic-like sense with certain combinatorics, with certain period and certain combinatorics. And so now it is just gives now understanding where to look for once renormalizable maps. Once renormalizable maps correspond to little copies of the Mandelbrot set. So we can sort of encode combinatorics of the map by the copy itself. We say that some map is renormalizable with combinatorics M0. Then its renormalization is renormalizable with combinatorics M1 and period P1. Then this normalization is normalizable with combinatorics M2 and period P2. So if the map is infinitely normalizable, we have this sequence of little copies with attached periods to them. And that is what we call combinatorics of the original infinitely normalizable map. Combinatorics. And from this point of view, today, the MLC conjecture was reduced to the conjecture which says that combinatorics of an infinitely normalizable map determines the map itself. So if you take the quadratic polynomial, which is renormalizable, infinitely normalizable with these combinatorics, so you select your favorite string of little Mandelbrot copies, and arbitrary string is admissible here, and then there is one and only one parameter, that is the conjecture, one and only one parameter, which which is infinitely normalizable with these combinatorics. It sounds very much in spirit as a rigidity, most of like rigidity phenomenon in geometry, and actually this dynamical MLC conjecture is very, very intimately related to the rigidity phenomenon. Okay, so why it was, how it was reduced to this? Well, why all these are related, I will not be able to explain you in detail in this talk, but at least, so there is, I should quote here the result by Yakos in the 90s. It is the result which was part of his Fields Medal quotation. And it says that if the map f sub c, its quadratic polynomial, is not infinitely normalizable, that Mandelbrot set is locally connected at this parameter. And so the MLC, due to the work of Yakos, the MLC conjecture was reduced to the situation, to analyzing the situation when the maps are infinitely normalizable And in this infinity normalizable case, one can reduce it to this kind of rigidity statement. Then combinatorics of the map determines the parameter itself. So, okay, so let me just state one of the results in this direction. As I told you, the conjecture is still open. That is one of the results, so which is obtained jointly with Jeremy Kahn. Many of you know Jeremy. He was around here for a good 10 years. And that was one of the biggest projects he was working on those days. And so that is our result in this direction. So if we take combinatorics, which stays, so we have this sequence of little copies of the Mandelbrot set, and if we assume that all these copies stay away from the main cardioid of the Mandelbrot set, so we look for all these copies. There are plenty of copies. We don't want this copy. It's just attached to the main cardioid. We don't want this. But we don't want also some copies which are not attached, but very close to the copy, to the main cardioid. That is our main cardioid. We want to stay away from the main cardioid. And as long as we take any copy, sequence of copies which stay away from the main cardioid, then the corresponding infinity normalizable map is rigid, and so the Mandelbrot set is locally connected at this point. And in particular, if we consider consider the copies which are symmetric with respect to the real line, then there is only one problematic copy, this one corresponding to the doublings, the biggest one, and all others are allowed. So for these copies which are symmetric with respect to the real line, and take any choice of copies, and the corresponding infinity normalizable map will be rigid. The Mandelbrot set will be locally connected at the corresponding parameter. And this brings us to, this statement brings us to the real line. And so let me tell you now what happened on the real line. So we now discussed this complex quadratic family. I give you some idea of one of the main conjectures for the complex quadratic family and where they stand at the moment. So now let us go to the real quadratic family. And in the real case, the situation is nearly complete. At least for the real quadratic family, it should be considered to be complete. So what is going on now? So we change notations. Z becomes X, so we're on the real line. So, and now C is on the interval. It is just the real slice of the Mandelbrot set. It is interesting parameters, range of parameters. For these parameters, there is an invariant interval, and we want to understand the dynamics on this interval. And there was the same conjecture, sort of real version of the Fatou's conjecture. Then for these parameters, hyperbolic maps, those maps which have an attracting cycle, are dense. And this conjecture was proved in the 90s here in Stony Brook. It is really true. And this conjecture, so though I cannot give you a real idea how it was proved, but so the upshot that it was proved by using plenty of complex methods. And the key difference why the situation here is better than the situation in general complex situations, that a priori bounds are easier to prove in the real case. Complex a priori bounds are easier to prove in the real case. And that is why in the real case one could go all the way to the density or to proof of the Fatou conjecture. Okay, so let us look at these hyperbolic maps. It's another iconical picture in this field. It is a picture of the real quadratic family. So instead of that picture, boring picture on the board, we have this real quadratic family. Here is the interval. It is 1/4. It is 1/4. That is -2. That is our parameter interval. And what is depicted vertically is basically the attractor for this dynamical system. So here we have a fixed point attractor. Then we have periodic point of period 2, this Dublin bifurcation action. Then we have attracting periodic point of period 4, etc. This cascade of Dublin bifurcations. Here we have a periodic point, attracting periodic point of period 3. It is hyperbolic. This hyperbolic window corresponding to attracting periodic point of period 3, etc. You see these windows all over the place, but it's not at all obvious that they're dense. You have quite black regions here and quite black region here. It's not at all obvious that these white hyperbolic windows are dense. And there is actually a very good reason why it is not so obvious. That the complementary parameter set is also big. It is big not topologically, it is nowhere dense topologically, but it is big measure in the measure theoretical sense. It is a theorem proved by Jacobson in around 1980. So, and he proved that stochastic parameter values have positively back measures. So what are the stochastic parameter values? Stochastic parameter values, the map is stochastic if it has an SRB attractor. So this attractor which governs behavior of almost all points. But in this one-dimensional situation, everything becomes more elementary. This condition is just equivalent to saying that f has an absolutely continuous invariant measure. That's all. Remember that SRB is related to some absolute continuity in the unstable direction, but here we have only this unstable direction. So what Jacobson proves that there is a set of parameters of positive measure for which the map has an absolutely continuous invariant measure. And so, for instance, this -2 is a density point for this set of stochastic parameters, and that's why everything looks so darkish here. So the hyperbolic maps, though they are dense, they occupy very small portion of the parameter space. Okay, now we have these hyperbolic parameters, or regular parameters as I call them, where there is an attracting cycle and almost everything converges to this attracting cycle. We have stochastic parameters for which there is an absolutely continuous invariant measure that governs behavior of almost all orbits. Do we have anything else significant, physically significant in this picture? So, and it turns out that that is it. From the point of view, from the measure theoretic point of view, that is all that we have. And there is this regular stochastic dichotomy, which says that for almost all parameters C, the corresponding real quadratic map is either regular or hyperbolic, so there is an attracting cycle which attracts almost everything, or it is stochastic, there is an absolutely continuous invariant measure, and which governs behavior of almost all points. So that is the result which, from this Kolmogorov's point of view, gives a good understanding of what is going on in this quadratic family. I should say that, well, again, this result has been proved, was proved, so essentially by complex methods, and still, so it is very involved. It's altogether, it is like 7 papers, maybe altogether like 500 pages. Then it was simplified. Now it is shorter, but still it is a few hundred pages altogether. Okay, so but you can wonder. So so Kolmogorov insisted that we should consider a typical family. So and here we have this quadratic family. Well, maybe this quadratic family is so special because it is a global holomorphic family. We can use the whole power of holomorphic machinery and prove something very special about some very special family. It turns out that it is not at all the case, and the quadratic family is actually, in a way, universal family. The universal family. And here is the result, which is a manifestation of this universal role of the quadratic family. So this result was obtained by, jointly with Arthur Avila and Wellington de Mella. So Arthur, probably many of you know Arthur as well. He was visiting the AMS many times and basically grew up here. And so first time he visited was when he was 20 years old. And this theorem came from those days. And I'm sure that you will hear quite a bit about this brilliant guy. So anyway, the theorem that we proved those days was that this regular stochastic dichotomy is still true for any non-trivial real analytic family of unimodal maps. So unimodal means just maps with one extremum, which look like this parabola, but just not quadratic, but with the same shape. That is the meaning of unimodal. And non-trivial means just that combinatorics of the maps changes in some way, that just it is not the boring family, so that all the maps are conjugate in this family. So it is, I think, so that is exactly the theorem in the spirit of this Kolmogorov's philosophy. We have generic family, and in this case it is generic in a very specific, strong sense. So it is just non-trivial, and in this family we understand, from the probabilistic point of view, we understand behavior of almost all orbits for almost all parameters. That is what Kolmogorov wanted, and it is a kind of first occasion this unimodal setting, analytic unimodal setting, is the first occasion when this philosophy was really carried through. And so what it has to do with the quadratic family. It is, the way it is proved is not that we repeat the argument for the quadratic family. It would be too difficult. Quadratic family is too special. But we transfer the results from the quadratic family to generic analytic families. So here is imagine the space of unimodal maps. And imagine this is quadratic family, our friend f sub c. And imagine some other family. And there is a natural holonomy from one family to another family through the topological classes of maps, just classes of topological conjugacies. And what we have proved that these classes are actually analytic submanifolds, codimension one analytic submanifolds, and the holonomy is sufficiently regular, though it is not smooth, but it is sufficiently regular to carry the theorems, as I suggested, from one family to another. So we proved this result about global structure of global foliated structure of this space of unimodal maps, and then just transferred the result from the quadratic family to a generic real analytic family. Okay, so let me step back a little bit, so let me go back to this theorem. So a very big part of this theorem is justification of the renormalization conjecture, which was put forward in the 70s by Feigenbaum, Collier, and Rarr. And it was proved in the 90s by Dennis Sullivan, McMullen, and myself. And so in series of papers, it's not a joint work, but it was a series of works, so altogether, which proved this normalization picture, as I depicted this strong normalization picture that I suggested in the beginning, but in this particular case of quadratic-like, in this particular quadratic-like unimodal setting, it was established. And it is big part of this results. So let me not go to this more technical formulation of the normalization conjecture, which was important here. But let me now try to tell you just a little bit what I mean by the universal small-scale structure. So what kind of universal small-scale structure comes out of this picture? So, so let us take a real Feigenbaum map, so some map which is infinitely normalizable, say with period 3. Infinitely every time, every normalization, it is stationary combinatorics with period 3, for instance. Then a kind of it was known since 70s. It is that such a map has a counterset which is 70s, 80s, maybe since 70s, I think that there is a counterset which is a global physical attractor which attracts almost everything. The dynamics on this set is easy dynamics. It's just group transformation, so it is endowed with some canonical measure, higher measure on this counterset. All this is fairly simple statements, but and they have basically they don't need normalization theory at all. But what needs normalization theory, and what is more or less equivalent to this normalization picture, at least one half of this normalization picture, is that the geometry of these counter attractors is universal. So, namely, so we have two maps like that. Let us consider two maps like that. We have counter attractor for one of these maps. We have counter attractor for another. These dynamics are topologically conjugate. So a priori, this is just a homeomorphism. And usually in dynamics, this homeomorphism has very poor smoothness. It is at most Hölder. So it is really usually would not anticipate much, maybe absolutely continuous. In this case, it turns out that this homeomorphism is actually C1 plus alpha. And this is intimately related to this normalization picture, that is the fact that these maps converge to the fixed point exponentially fast, basically equivalent to saying under normalization to say that they converge to the fixed point exponentially fast, basically equivalent to this rigidity statement for this counter attractor. So the small scale geometry of this counter attractor is universal. Also, it was completely new phenomenon in the 70s when it was suggested by Feigenbaum, Collier, and Rarr, and universality phenomenon, and also very intimately, very closely related to the rigidity, most of rigidity phenomena. Okay, so where we are going now? Now I promised to go from dimension 1 to 2. So, well, you see that in dimension 1, basically, with this theorem, so at least in the unimodal case, when there is one extremum, the picture is complete. At least analytic unimodal case, the picture should be can be considered to be complete from this Kolmogorov's point of view. So what happens in dimension 2? In dimension 2, the situation is much less complete, to say the least, but there are some developments. So, and one of the great developments was the work of Benedicts and Carlisson, the breakthrough by Benedicts and Carlisson, who justified existence of Henon attractors. So now we consider the Henon maps. It is now, at this moment, it is just polynomial automorphisms of R2. So B is a Jacobian, this new parameter B is a Jacobian of this map. So if B is small, you can consider this is a little perturbation of the quadratic map, of the one-dimensional quadratic map. So there is a non-invertible one-dimensional quadratic map, and you perturb it to so invertible two-dimensional dynamical systems. And Benedicts and Carlisson, and then followed by other people, they proved that there is a set of parameters, CB, set of parameters of positive measure, such that the corresponding Henon maps have attractor, SRB attractor. So this attractor, which was observed numerically, actually mathematically can be justified, at least for some very small Jacobians. So, and it governs the behavior of almost all points. I sort of depicted here somehow. Just here is the parameter which is perturbed, -2. It is one-dimensional. It is one-dimensional slice, and here there are these Carlisson-Benedicts parameters of positive areas. Yeah. By the way, notice that we have a horseshoe here. This Henon map looks also like the familiar horseshoe. The only difference here that in the Smails horseshoe the tips goes outside, and here the tips is inside, and it is the huge difference. So Smail horseshoe is a fully understood picture. This horseshoe, Henon horseshoe, is a very poorly understood picture, but it was a great breakthrough towards this kind of fundamental conjecture, as I described. So there is another part of the parameter domain. How about timing? So do 10 more minutes. Thank you. So, okay. So there is another part of the parameter plane, which it is our parameter plane C and B, that is Jacobian parameter. So that is C, it is our familiar one-dimensional family here, sits here. That is our familiar Feigenbaum parameter, the limit of Dublin bifurcations. And there is an interesting analytic curve sticking out of this Dublin bifurcation. And the maps on this analytic curve turns out to be infinitely normalizable in the Henon sense. So the Feigenbaum parameter is infinitely normalizable in the unimodal sense with Dublins. And now we have renormalization, which can be defined for Dublin normalization, which can be defined for Henon maps. We have just two domains which are permuted. And then when we rescale it, actually nonlinear rescaling is needed here. Then we obtain a Henon-like picture again, and then we can continue and continue. And what we proved here with our colleague Marco Martins and Andrea de Carvalho, who was also a postdoc here. So we proved that if maps are infinitely normal, that such maps exist, they fill in. So there is some little this curve C filled with such kind of infinitely normalizable maps. And for these maps, there is a physical attractor, a counter-physical attractor. And we anticipated that this physical attractor has the same rigidity structure as in the unimodal case. And we were extremely disappointed that actually it is not the case. So the geometry of this physical attractor does depend on the Jacobian. It does depend on the Jacobian. So the map can be, the conjugacy can be only Hölder continuous, not Lipschitz, if the Jacobians are different for different maps. And so the situation for some time looked quite desperate. And again, the probabilistic point of view saved the day. It turns out that probabilistic rigidity still holds. So these counter attractors, they are rigid almost everywhere with respect to the canonical measure on these counter sets. So from physical point of view, it is good enough. So if you go to this counter attractor, and that's what people saw, that the geometry is still universal. So just experimentally, and it is because there is a probabilistic rigidity. So that is probably the way how this rigidity philosophy should carry from dimension 1 to dimension 2. So now it is that much as I would like to say about real dimension 2. So we have this Henon map in the real dimension 2. And now a few words about complex dimension 2. It is also a big field, and we have here now Eric Bedford, so who one of the classics of this field. And I have, of course, in 3 minutes, I cannot give an overview of this field. But so I would like to formulate one recent result in this field, which is related to the beginning of our discussion. Okay, so first of all, one step back to the one-dimensional, complex one-dimensional situation. It was proved in the 80s that the J stability on the Julia set, is a generic property. So we don't know whether hyperbolicity is dense, but we do know that the parameter values for which the Julia set moves continuously, these parameter values are dense in the parameter space, and this is nothing else, is the interior. One can show that the interior of the Mandelbrot set is filled with stable parameters. We don't know whether these parameters are hyperbolic or not, but nevertheless, they're always stable. However, in dimension 2, there is this Neuhaus phenomenon which destroys it. So we cannot have a generic stability in dimension 2. So, but it was a conjecture by Paris in the real setting, who suggested that Neuhaus phenomenon and related homoclinic tangency phenomenon are the only abstractions. So it is the only enemy which destroys the stability and destroys hyperbolicity. And so without going to details, we confirmed this conjecture in the Henon setting. It's a very recent result with Romain Dujardin. So, and finally, so in the final couple of minutes, I would like to go back for a second to dimension 1, again, complex dimension 1. How about attractors, physical attractors in the complex dimension 1? And are there any interesting physical attractors in the complex dimension 1? And of course, it can happen, interesting physical attractors should sit in the Julia set. And so if to have such an attractor, one should have a Julia set of positive area. And for a long, long time, it was assumed that all Julia sets have zero Lebesgue area. It was a conjecture also going back to Fatou, actually, that all Julia sets must have zero Lebesgue area. And it was fairly recently in still, no, it's put 90s, it should be 2000. It's about 10 years ago. Sorry, it's a mistake. So Buff and Chirita so carried out in a remarkable way a program which was set by Doherty to construct first examples of Julia sets of positive area. However, there is a drawback in this construction. So these Julia sets topologically are very wild. So it is very difficult to understand topology of this Julia set. There are no models, topological models, and they are invisible. Somehow they have positive measure. You would assume that they should be visible, so it is easy to see them. But the problem is that the parameter set constructed in this by Buff and Chirita is so small that you cannot localize actually and to see, visualize these Julia sets of positive area. And it is very recent development already, also joined with Artur Avila. We constructed examples which we call black holes of Julia sets of positive area of different nature. So they are tame, the Julia sets admit precise topological model, and it is easy to localize corresponding parameters and probably not so difficult to visualize this set, and the set of parameters is fairly big. So, and this result requires, actually both this and this requires actually to invoke 4 different normalization theories. So, and here is finally the picture of related to our black hole example. So what you're watching now, what you're seeing now is a black hole. So it is actually quadratic-like map. So we have some quadratic polynomial, big quadratic polynomial. So and it is quadratic-like renormalization for this quadratic polynomial. So which is a black hole in the following sense. It's extremely difficult to escape from here. There are these Hawkins rays. You see, they can escape it, never come back. But they're very, 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 very skinny. So it is very difficult to escape. There is very low probability of escape from the black hole and very big probability to be sucked by the black hole. And so most orbits will be sucked and go further and further to deeper and deeper and deeper scales and will converge to the physical counter-attractor, producing the Julia set of positive areas. So if you did not believe in black holes, so that is the proof that they exist, but be careful, it is dangerous, so you can be sucked. Okay, thank you very much.
Well, you said the hyperbolistic phenomenon is related to Moser rigidity.
So you see that to prove hyperbolicity, at least the way it has been done so far. So it is to prove this kind of rigidity statement that you have quadratic polynomial with a given combinatorics. You can define combinatorics. Well, I defined it in infinitely normalizable case. You should prove that this combinatorics uniquely determines the parameter value. It is equivalent at this stage of the development. It's equivalent to MLC conjecture, and this would apply density of hyperbolicity. And this conjecture just manifestly rigidity type statement, most of type statement. It's manifestly most of type statement, but there is a deep connection actually. There is really a deep connection.
Why?
Why? You ask why.
Well, this is my question.
You ask why it is related. I can say in this way maybe that there is this dictionary which is called Sullivan's dictionary.
I know him.
So you know him. That's why you are that is a motivation for your question. So between the issues, this halomorphic dynamics in the sense I have described here, and the theory of Kleinian groups. So, and the theory of Kleinian group is group of Möbius transformations of the Riemann sphere. So it is some kind of dynamical system, but the time is a group. So, and there is a very close connection between these. But so but rigidity statement for Kleinian groups, it is most of rigidity. So through this dictionary, so it is becoming more motivated.
Yes. Does one get anything at all like this if you use continuous time instead of discrete time?
So if to use continuous time, well, you should go basically to dimension 3 for continuous time. So the idea would be that if you consider three-dimensional phase space, and you just consider two-dimensional return map, so Poincare return map, then you will obtain something like this Henon maps or this type of maps. And so studying two-dimensional dynamics, discrete dynamics, is basically the same as to study three-dimensional continuous dynamics. So you should observe the same type of phenomenon, but in one dimension up.
Any other questions? Okay, so let's thank Misha again.
Thank you so much.